Lesson: Selecting and Training Machine Learning Algorithms. Selecting and training machine learning algorithms is a critical skill for professionals aiming to implement AI models effectively. The process involves understanding the nuances of various algorithms, their applicability to specific problems, and the intricacies of training them to achieve optimal performance. This lesson delves into practical strategies, tools, and frameworks that help in navigating these challenges, emphasizing actionable insights that professionals can apply directly in real-world scenarios. Machine learning algorithms can be broadly classified into supervised, unsupervised, and reinforcement learning. Supervised learning involves training a model on labeled data where the desired output is known. This is particularly useful in applications like classification and regression. Unsupervised learning, on the other hand, deals with unlabeled data and is used for clustering and association tasks. Reinforcement learning is a type of machine learning where an agent learns to make decisions by taking actions in an environment to maximize cumulative reward. Selecting the right algorithm is the first step. Considerations include the nature of the data, the problem domain, and the computational resources available. For instance, decision trees are intuitive and effective for small to medium-sized datasets, while support vector machines are powerful for classification tasks with clear margins of separation. However, SVMs can be computationally expensive for large datasets. Random forests, an ensemble method, mitigate overfitting by averaging multiple decision trees, offering robustness and accuracy. Training machine learning algorithms involves preparing the data, choosing the model architecture, and optimizing the model's performance. Data preparation is crucial and includes cleaning, transforming, and splitting the data into training, validation, and test sets. Tools like Pandas and NumPy in Python are invaluable for manipulating data efficiently. A well-prepared dataset ensures the model can learn effectively and generalize to new, unseen data. Hyperparameter tuning is an essential aspect of training machine learning models. Hyperparameters are external to the model and set before the learning process begins. They include parameters like the learning rate, number of trees in a random forest, or the number of layers in a neural network. Techniques such as grid search and random search are commonly used for hyperparameter optimization. Grid search exhaustively searches through a specified subset of hyperparameters, while random search randomly samples from the hyperparameter space. Although grid search is comprehensive, it can be computationally expensive. Random search, on the other hand, is less exhaustive but often finds good solutions faster. Implementing AI models also involves leveraging frameworks that streamline the development process. TensorFlow and PyTorch are two popular deep learning frameworks. TensorFlow, developed by Google, offers robust tools for deploying models in production environments. Its high-level API, Keras, makes prototyping easy and efficient. PyTorch, favored for its dynamic computation graph, allows for greater flexibility and is often used in research settings. Both frameworks provide tools for model visualization, debugging, and deployment, which are critical for complex AI workflows. A case study illustrating the selection and training of machine learning algorithms is the use of convolutional neural networks in image recognition. CNNs, a class of deep neural networks, have revolutionized image classification tasks. They are designed to automatically and adaptively learn spatial hierarchies of features from input images. A practical example is the ImageNet Large-Scale Visual Recognition Challenge, where CNNs achieved significant improvements in accuracy over traditional methods. The architecture of CNNs, with convolutional layers, followed by pooling and fully connected layers, is specifically suited for capturing the spatial and temporal dependencies in images, making them ideal for image-related tasks. However, training deep learning models like CNNs requires substantial computational resources. This is where cloud-based platforms such as Google Cloud AI, AWS SageMaker, and Microsoft Azure Machine Learning come into play. These platforms offer scalable computing resources, enabling the training of large models without the need for local hardware investment. They also provide integrated tools for data labeling, model training, hyperparameter tuning, and deployment, making them indispensable for machine learning practitioners. Another critical aspect of training machine learning models is the evaluation and validation of model performance. Metrics like accuracy, precision, recall, F1 score, and area under the receiver operating characteristic curve are used to assess classification models. For regression tasks, metrics such as mean absolute error, mean squared error, and R-squared are commonly used. These metrics help in understanding the strengths and weaknesses of a model and guide further tuning and improvement. Cross-validation is a robust technique for model evaluation. It involves splitting the dataset into multiple subsets, training the model on some subsets while validating it on others, and rotating through the subsets. This approach provides a more reliable estimate of a model's performance compared to a single trained test split, as it reduces the variability associated with random partitioning of data. The deployment of machine learning models is the final step in the AI workflow. Once a model is trained and validated, it needs to be integrated into a production environment where it can interact with live data. Tools like Docker and Kubernetes facilitate the deployment process by allowing models to be packaged into containers that can be easily scaled and managed. Continuous integration and continuous deployment pipelines can automate the deployment process, ensuring that models are updated and maintained efficiently. An example of successful deployment is the recommendation systems used by companies like Netflix and Amazon. These systems analyze user behavior and preferences to suggest relevant content or products, significantly enhancing user experience and engagement. By employing collaborative filtering and deep learning techniques, these organizations have developed sophisticated models that operate at scale, processing vast amounts of data in real time. In conclusion, selecting and training machine learning algorithms is a multifaceted process that requires a deep understanding of the algorithms, careful preparation and manipulation of data, and the utilization of advanced tools and frameworks. The choice of algorithm is influenced by the problem domain, data characteristics, and resource constraints. Training involves data preprocessing, model selection, hyperparameter tuning, and performance evaluation. Finally, deployment ensures that trained models deliver tangible benefits in real-world applications. By adhering to best practices and leveraging modern tools, professionals can develop robust AI models that drive innovation and efficiency across various industries.